There are physical systems that oscillate that when I apply Newton's second law to their solution, they begin to give me a taste of the harmonic oscillator differential equation here, x double dot plus omega squared x is equal to 0, where omega, of course, is the angular frequency of the oscillator. We're going to see this happen in each of several examples I'm going to do. I'll do as many examples as I have time for. A classic of our physics is the motion of a pendulum. Not only are we all aware that a pendulum is an oscillating system, because it swings back and forth periodically with a time period and a frequency and so forth, we also know that it's been of great service to mankind as a timekeeping device. We built clocks for a very, very long time, where the periodicity of the clock, counting out the seconds, was done via a pendulum. Of course, now we do such things electronically and in some nuclear cases and stuff like that, but the pendulum has a great history. So what I'll do is draw the simplest pendulum that I can imagine here. I have a support that I can hang my pendulum from above, and my pendulum is nothing more than a mass on a spring, on a string. Let's say the string is of length L and the mass is of length M. And what I'm going to do, of course, if I just hang it vertically, it hangs there and doesn't do anything of any particular interest. But what I'll do is I'll draw it back from its equilibrium position, the vertical hanging position, by a certain angle theta. And then I'll release it from rest. And what a pendulum will do for me is swing back and forth under the influence of the force of gravity and its motion determined by also the force of the tension in the rope that supports it. So I'll begin with a free body diagram of this motion. I'm going to draw it according to my need of finding a component of force that is drawing the pendulum back to its equilibrium position. In the case of my harmonic oscillator mass on a spring problem, it is the force of the spring that is restorative. In this case, it's gravity that causes the restoration. So for my free body diagram, I'm going to draw the tension along the direction of the rope, the supporting rope, and a component of the weight. This is very familiar to me because it looks a lot like inclined plane free body diagram, mg times the cosine of theta. These two forces, tension and mg cosine theta, are not in equilibrium with each other because the motion of the pendulum is quite circular, isn't it? And so there's centripetal acceleration associated with this motion. Those forces are not equal. But the tension force minus mg cosine theta would be equal to mv squared over r, but that's not the analysis that I'm interested in. The analysis that I'm interested in is this force, mg sine theta, which is the force that is producing the motion back toward the equilibrium position for the pendulum. So as such, I'm going to write Newton's second law for the pendulum moving under the influence of these forces. I'm going to write Newton's second law for the pendulum under the influence of these forces. Now I have two options here of how I can write this Newton's second law. I can write it as an angular Newton's second law, that is, I can write Newton's second law for rotation, or I can write Newton's second law for translation, as the mass translates along the arc. I can do it either way. And as an aside, later on, you might want to do it. I haven't even decided yet. I'm just talking about it seconds before I decide. You might want to take a piece of paper later on and demonstrate it the opposite way. They are, of course, equivalent to each other. Let me do it by writing Newton's second law for rotation. That's how I choose this morning on a whim. That the sum of all the torques is equal to the moment of inertia of the thing multiplied by the angular acceleration. I choose that one because it's very easy for me to describe the position of the oscillator in the context of the angle theta, which it is drawn from its equilibrium position, and I'm not wild about the curved arc and describing the velocity along the arc or the acceleration along the arc, so I choose not to do that. So what is the torque? Well, the tension acts towards the axis of rotation, mg cosine theta acts away from the axis of rotation, they exert no torques. The only torque is exerted by mg sine theta, and that torque is that force multiplied by the moment arm, which in this case is the length of the string. So this is going to be, if you pardon me changing the order on you, mgl times the sine of theta, pardon me. And I'm changing the order just because I like my harmonic function here to be the last thing on the equation there. So I've moved the L in a little bit, but that is a force multiplied by a length, which is naturally a torque. Now the moment of inertia, I'll treat this mass as a point particle at the end of that string, and I know that the moment of inertia of a point particle is going to be equal to mr squared. Well, r in this case is the length of the string, so I'll write that as ml squared, multiplied by alpha. Alpha is the angular acceleration. That is, it's the second derivative of the angular position with respect to time. So I hope you won't mind at all if I write this as theta double dot. We see where I'm going with this, right? We see what's happening. Well, I see very conveniently that there's, here's another thing that I'm going to do. I'm glad I caught this just before I did any algebra. The force that appears on, or the torque that appears on the left-hand side of this equation, I'm going to make it negative. Shadi, you can't do that. You can't just make it negative. Yes, I can. Because I choose by coordinate system which torques are positive and which torques are negative. But I want to point out to you this very important fact, and it's true of all oscillating systems. It doesn't matter whether I call this positive or negative. That is, it doesn't affect the solutions. And the reason why is that after the pendulum swings down to equilibrium position, going past it out the other way, then that torque will then be in the opposite direction. So at some point during the oscillation, the force that is the cause of the oscillation will change sign. Consider the mass on the spring. When I first pull it away from equilibrium position and release it, if I pull it to the right, then the force is in the negative direction, but once it starts to compress the spring after traveling through equilibrium, now the force is directed to the left. So the force changes sign during the motion. So I just artificially added a negative sign there because I find the algebra of it appealing. So I can cancel the m's on either side of the equation and one of the l's. And now I'm going to do a very traditional sort of harmonic oscillator algebra here. And I'm going to add everything over to the other side. So I have L times theta double dot plus G times the sine of theta is equal to 0. And then I'll divide through by L. Theta double dot plus G over L sine theta. Now, working with harmonic oscillator problems is very often done by inspection. You get your differential equation and say, if this is a harmonic oscillator differential equation, I already know what the solutions are. Once you know the solutions to a particular differential equation in our science, once you know those solutions, you don't have to solve it all over again every single time. It's like once we're done with our physics and you go on and you see viscous drag, it's okay to say, well, I know viscous drag when I see it. It has solutions like this. There's no need to solve the differential equation over and over again. So I look at this and say, well, harmonic oscillator differential equation. No, because look, here is my fundamental harmonic oscillator differential equation, x double dot plus omega squared x equals 0. I love it. Here, the coordinate is theta instead of x. That's fine. Doesn't matter what you call it. So x double dot, theta double dot, great. A constant, great. X sine of theta. That is not the harmonic oscillator differential equation. That does not have harmonic oscillator solutions. Oh well, except that if I limit the angle theta, that is the angle that I initially draw the oscillator back to, if I limit that angle to small angles, I can invoke the approximation that for small angles, the sine of theta is approximately equal to theta. For small angles. And remember, in the first oscillator lecture, I made a whole argument about how almost all motion is harmonic. Well, all bound motion is harmonic for small displacements from equilibrium. So now I'm saying don't let the pendulum go too far. Just let it go a little bit and swing back and forth. If I make that assumption that the sine of theta is approximately equal to theta, you immediately see what happens. If you're following along, you're certainly ahead of the words that I'm saying. That theta double dot plus G over L times theta is equal to 0. Now by inspection, yes, it is the harmonic oscillator differential equation because it has x double dot, theta double dot, a constant, theta, or x theta, that's good, is equal to 0. Yes, it's the harmonic oscillator differential equation. I do not need to write it again. Now, I can write the angular position of the oscillator as a function of time. Theta, as a function of time, will be equal to the maximum displacement. What are we going to call that? I don't know, theta naught? Is that okay with you? I just made that up. The initial angle, right? The initial angle you draw it back to, right? Times the cosine of omega t. Well, what's omega? You mean square root of k over m? No. Omega is the square root of k over m for the mass on a spring. What's omega here? Well, I can tell by inspection. In my harmonic oscillator differential equation, omega squared is that constant, which means omega in this case, I'm just going to write it over here, that omega in this case, by inspection, omega must be the square root of G over L. By the way, this is something that Galileo famously realized. He was in a church watching some, I suppose, oil lamps sway hanging from the church ceiling. Now, in principle, they all have different masses because they have different quantities of oil in them and whatever, and he realized that they had the same time period independent of their mass. Well, this is realized here because the angular frequency is naturally related to the time period in a very simple way. So once I have the angular frequency, I in principle have the time period, there it is. So the time period does not depend on the mass of the pendulum. It only depends on the length of the pendulum and the planet that you're on. By the way, a little aside here, this is how I measured the acceleration due to gravity. Some of you who took an earlier physics course remember me talking about my measurement of the acceleration due to gravity, where I built a 3-story tall pendulum, displaced it small displacements from equilibrium, and let it swing. Well, all I need to know is the length of the pendulum and the time period of the pendulum, and I can measure the acceleration due to gravity very precisely. And what is the number that I got? It was 9.822 plus or minus 0.006 meters per second squared. I was able to obtain that by building a very large pendulum. That's an aside. Concern ourselves with that now. So when I write omega t here inside for my cosine, I'm going to get rid of that bracket, write this as omega t. When I say omega, what I specifically mean is the square root of g over L. I realized that I didn't want to write the square root of g over L there because it's not very compact notation. So omega is the square root of g over L, and it goes like that. And then the angular displacement omega. Look, I have a problem. I have the angular displacement omega and the angular frequency omega. Watch out for that. It's dreadful, dreadful, dreadful stuff. I'm going to have to write it in now. I've caused the problem for myself. Omega, the angular velocity of the pendulum, is going to be the initial angle multiplied by the square root of g over L times the cosine sine. I'm really making a mess of this, aren't I? Really making a super mess of this. I shouldn't even have started. I'm just making this stuff up anyway. Everybody knows that. So let me try again. The angular velocity omega. Sometimes what I'll do is I'll call the angular velocity capital omega in order to get myself out of this particular problem that I have between the angular velocity of the mass and the angular frequency of the motion. But omega is equal to, I did it again, pardon me. I need a negative sign, negative theta naught. That was my problem all along. The square root of g divided by L times the sine of the square root of g over L times t. So now I have the angular velocity as a function of time. Another derivative gets me the angular acceleration as a function of time, and so on through the thing. So this is the solution of the simple pendulum, and it comes not by resolving the differential equation, but by recognizing it as, in approximation, simple harmonic motion. So now, for another example, and let's give this thing a name at the end. I don't immediately have a name for it. But what I'm going to do is I'm going to take a mass. Like this problem is sometimes presented as a soda can. I take a soda can and I put it in some water. Now, when I put it at the surface of the water, it sinks down into the water, but then eventually it gets to a point where it will float in the water. So now I have a can floating in the water, and then if I just poke it, give it a little displacement from equilibrium, it will bob up and down in the water with sort of a periodic motion. I wonder about that motion, so I'd like to investigate it now. So by way of a diagram, I'm going to have the surface of a fluid here. I'll make some waves just so we know what we're talking about. And then I'll have a can, which is sitting in the water. I suppose it's sitting at this point in the equilibrium position. Now, why does it float? Well, it floats under the influence of a buoyant force. It is literally water pressure pushing upward on the can. If you go through the analysis, and I'm not going to go through it right now because it'll distract me from solving the problem, which you appreciate that what I'm saying is true. If you would like to research it more on your own, you can do that. The buoyant force upward on the can is equal to the weight of the water that the can displaces by its volume. Now, for example, we all, every once in a while, go for a swim, and you know that human beings have a density roughly 1, a little bit higher, which is why you tend to sink until you bloat, and then you float. And our density is in the vicinity of 1, but it changes, and you can alter your density. For example, you can be in the water, happily floaty, enjoying yourself. If you try to raise your hands out of the water, you sink immediately, and the reason why is that your volume of your arms is no longer displacing that water, and now the buoyant force on you has become less than your weight, and you sink. In fact, in order for you to simply float without any effort on your part, most of your body has to be immersed because your density is very nearly the density of water. You may have heard of folks going to bodies of water on Earth where the water is very, very salty, which increases the density of the water, like Great Salt Lake or the Dead Sea. And people just throw themselves in, and even if you can't swim, you float guaranteed because your density is much less than the density of the water. So when you displace water by your volume, the weight of that water that you have displaced is greater than your own weight, and so you are buoyed up by that. So appreciating the fact that the upward force that is exerted on the thing, the buoyant force, is equal to the weight of the water displaced. I'm going to do a little Newton's law to this. Well, free body diagram style, I have a weight force mg that is directed downward. And then I have a buoyant force upward. I'm going to call this FB, the buoyant force acting upward on the can. Now, I'm going to use a little wisdom here. I have already demonstrated in the previous lecture that when I have a spring hanging vertically and I add a mass to it, the force of gravity, the constant force of gravity, only has the effect that it draws the mass down from its equilibrium position to a new equilibrium position. The same effect happens here. When I place the can in the water, the force of gravity acting downward pulls the can down into the water until the volume of the can that is below the surface of the water displaces a sufficient weight of water to be equal to the weight of the can. That is the new equilibrium position. So I set it in there, and it is stationary, and then I displace it from that equilibrium position by pushing it down some distance x. So there'll be some distance here, perhaps a small distance is most prudent here for this, x, that I push it down from its equilibrium. So the only force that I need to consider in my Newton's second law, I'm going to cheat a bit, because I know the effect of the constant force of the weight. I'm going to cheat a bit, and I'm going to ignore it in my Newton's second law for that reason. So writing Newton's second law, the sum of the forces that act on the can is equal to the mass of the can multiplied by its acceleration, which quite naturally I'll write as x double dot in the style of this physics that we're doing here. So what force am I talking about? Well, I'm talking about the buoyant force on the can. And I'm going to write that with a negative sign, and you know why? Because I choose in the coordinate system and in the algebra of harmonic oscillation, I like to have a negative sign so that when I stir it around to make it look like a harmonic oscillator, I want that term to be negative. Well, what's that equal to? Well, I have to compute it. It's equal to the weight of the water displaced by the volume. Well, the weight of the water is going to be the mass of the water displaced. So I guess call that mass of the water displaced multiplied by the acceleration due to gravity, right? That is going to be equal to the mass of the can, x double dot. You see, I've preserved the right-hand side here. Well, what's the mass of the water, or the mass of the water that's displaced? Well, that's the density of water, which I'll just call rho, the density of water, multiplied by the volume that's displaced, multiplied by g, is equal to the mass of the can, x double dot. The volume of the water displaced. Oh, I lost my negative sign. Thank you. I guess I need to have a negative sign there as well, and the negative sign persists here. That's good. Thank you. The volume of the water displaced is equal to the cross-sectional area of the can multiplied by the displacement vertically. That's how much water is displaced in terms of volume. So the volume displaced is going to be equal to rho. V is going to be the cross-sectional area times x. I'm going to take that x and move it to the end here, because I like to keep my equation organized in such a way that I see the dependence on the end. Yes, the density of water. I could in principle, but I wanted to, maybe I'm using a different fluid. Maybe it's motor oil. I've often wondered about, well, it doesn't matter, but I've wondered about filling a swimming pool up with olive oil and trying to swim in it. Oh yeah, it would absolutely be gross, but, well, any oil. I just thought that olive oil, maybe there'd be health benefits or something. I don't know. You want to do motor oil? I'll just collect used motor oil and I'll fill a pool with that. I don't know. I just thought olive oil would be nice. You could have bread for dipping in the swimming pool full of oil. Look, this is terrible for a recorded lecture. We're not doing this. But the fact of the matter is the density of the oil is less than the density of water. So how do you do swimming in a substance that is far less dense than you are? For example, try swimming in the air. Does not work. Works in cartoons, does not work in real life. Probably. So that's something I'm going to try a little later on. Now let me solve and try to get this into a harmonic, see if it looks harmonic oscillator. And so I'll mix it around so that I have x double dot plus rho a g over m x is equal to 0. Now, by inspection, yes, indeed, it is harmonic oscillation. I don't have to do any approximation at all. This is harmonic oscillation. And I could have suspected that right away. As soon as I realized that the force was linear, did you see that the force is a constant times x? Just like kx, I've got this rho a g times x. It's a constant times x, so of course it was going to be harmonic oscillation. There it is. But the winner here is that I know what that constant is, and I know what it stands for, because rho a g over m is omega squared, which means that omega is equal to, for this oscillator, is equal to the square root. And by the way, yes, I now know what the solutions are for the motion. But sometimes in harmonic oscillation, actually, I kind of feel like most times in harmonic oscillation, I am most interested in the frequency of the motion and not so much in the position as a function of time. And that'll become more apparent to you as you become more practiced in physics. This, of course, is equal to 2 pi divided by the time period of the motion. And so I can solve for the time period of the motion is going to be equal to 2 pi times the square root of the mass of the can divided by the density of water, the cross-sectional area of the can, in G. Now, I had said at the beginning of this, I don't know what to call it. Is it a can or is it something else? Imagine that it's a ship. And so I go down to the seafront here, and they've got some ships in the water there that I can tour and look at. And so I can go from one end of the ship to the other, and I can walk down the thing and measure out the length of the ship, and I can measure the width of the ship. Perhaps they've done me the service of having a plaque there that tells me the square footage of the ship, so I can know its cross-sectional area. So if I know the cross-sectional area of the ship, and I know the density of water, and Sarah's already pointed out to me that I do know that, and I know what planet I'm on, the acceleration due to gravity 9.8 meters per second squared at sea level, and I can stand there and watch the ship bob up and down in the water. And I can time that time period all day long, many time periods with a stopwatch, and stop my watch after hours of just sitting there watching the ship bob up and down in the water. Divide by the number of oscillations, I can calculate the mass of the ship, which is pretty cool for indirect measurements. This is one example of using harmonic oscillation for indirect measurement, but it is commonly done. When you have to measure things that are of extraordinarily small mass, measuring them putting them in some sort of harmonic oscillation context, by the way, also charges, very, very small charge, a lot of things. Put them in some context where there's harmonic oscillation, and you can infer their fundamental physical quantities based on the frequency of the oscillation. Right? So a thing that I can't put my hands on, I can shoot radio signals at or vibrations at, right? Laser beams at, whatever. Create some oscillation, and based on the frequency of oscillation, determine some fundamental quantity. If I just have some theoretical background. What do I call this thing? The Titanic. But it was a can I was talking about the whole time. What's that? Oh, the Cantanic. I thought you said Cantastic. I don't know if you've ever played in the summertime. We do this a lot at the pool. Can Jam. Is it? Really? It's not how I play it, but I'm right-handed, so. So now for my last example here, what I want to demonstrate for you is what is known as a physical pendulum. The first pendulum that I did for you today had some simplification. Notice that I didn't consider the mass of the string that supported the pendulum. Of course I wouldn't do that. I can always choose a string that's very light, and its contribution to the motion is what we can essentially call negligible. But that's not always the case. Imagine that I build a pendulum for a clock, for example, and the pendulum is a disc that hangs at the bottom. If you ever see a grandfather clock, very beautifully designed, it's a brass disc hanging at the end of a brass rod whose mass cannot be neglected. I'm sure that you'll all be thrilled to see the return of your friend, Space Peanut. Consider a pendulum constructed from an arbitrarily shaped mass, supported from a position here that I've just sort of chosen arbitrarily. The way that I've drawn it, imagine that there's gravity. I've drawn it so that so much of the mass is directed to the left that it clearly indicates that it will swing to the right, as a pendulum would. But how do I understand its motion? Because it's not like my pendulum. It doesn't have a length and a mass. I can't say that its frequency is associated with the length and the mass. What would I do? Well, consider the force of gravity acting on this pendulum, on this physical object. Where does it act? At the center of mass position. Let's imagine, and I'm just making this up, that the center of mass position is located there. I'm going to label it Cm. And so the force of gravity, mg, is acting at the center of mass position. This means that this force of gravity has two components that I can identify. A component that is directed radially away from the axis of rotation, which is naturally mg times the cosine of theta, and a component that is perpendicular to the line drawn, I guess we call it the moment arm, drawn from the axis of rotation to the center of mass of the thing, and that's going to be equal to mg sine theta. Naturally, there's some sort of structural force that acts at the pin along the radial direction, otherwise the mass would fall under the influence of gravity, but I'm not considering that. Because just like my pendulum solution, the force that matters to me here is the force that would return the mass to its equilibrium position. That is the mg sine theta force. I'm going to say that this object, this randomly shaped Space Peanut object that I've chosen, has a moment of inertia I, and that the distance between the axis of rotation and the center of mass of the system is capital D. Those are sort of customary choices when solving this problem. but I think they make an awful lot of sense. So how am I going to solve it? Well, naturally, because it's a regular object rotating, I'm going to apply Newton's second law for rotation, that is the sum of the torques is equal to the moment of inertia times the angular acceleration. And proceed quite rapidly because now I know how this works in this context. I have a torque exerted by the mg sine theta force, so that is mg d times the sine of theta. It's operating the same way as it did in the simple pendulum version, except now instead of L being the length of the pendulum, d is the distance between the axis of rotation and the center of mass of the system. Now I have a moment of inertia that is unknown. Once I have this solution, I can solve all problems of all moments of inertia. Rods, discs, hoops, whatever sorts of things I come across with different moments of inertia. Yes, again, I'm leaving out my negative sign that I choose here, so I'll write the negative sign. Thank you, quite arbitrarily. Alpha is theta double dot. Now I'm going to rearrange this, but I'm going to invoke the same thing I did in the simple pendulum solution. And I'm going to make the small angle approximation and suggest that the sine of theta for small angles is equal to theta, such that when I rearrange this equation, what I get is that theta double dot plus, and I have to look at all my constants that I have, mgd divided by the moment of inertia, I, multiplied by theta, is equal to 0. So I immediately see that the angular frequency of the physical pendulum that I've just described here is going to be equal to, reading off the coefficient in front, mg times d divided by the moment of inertia of the pendulum. You may look at this and say, oh my goodness, look, now it's mass dependent, because now the mass appears in the frequency. I think it's not actually mass dependent because the moment of inertia is always going to be of a form mr squared, whatever it happens to be, and that mass will ultimately cancel the mass in the numerator. So like its friend, the simple pendulum, the physical pendulum, it does not depend, has a frequency that does not depend on mass, but does indeed depend on how the mass is distributed in space. And you can easily imagine, I think, many, many problems that we can solve where I have an object of moment of inertia that oscillates. And we're going to call this the physical pendulum, and that distinguishes it from the simple pendulum that I demonstrated earlier in the lecture.